Hey, today we're going to be taking a look at the tangent line. Now the tangent line is a really big problem for us in mathematics. We're always trying to find out what is the slope at exactly one spot. So to start this off today, we are going to look at a curve, a simple curve like so. And I know at this point I can draw a line tangent to that. We learned that in geometry, that a line tangent to the curve touches the curve in exactly one spot. So if I know that this line is tangent, I know it's going to touch exactly in one spot. So the question that we want to find out today is, how do we find the slope of a tangent line? So before we do that, let's review what slope is. It is the change in y, delta y over delta x. Now, this is a really easy formula for us to use, but this still requires 2 points. I need 2 points to find slope. The problem with the tangent line, if I want to find the slope of a tangent line, we only want 1 point. So if I'm only looking at 1 point, my change in x, therefore, would become 0. And that's where the problem lies for us. So today, what we're going to find out is how Newton and another mathematician named Leibniz came up with the slope of a tangent line. So we're going to start off in a very much more thoughtful way to do this. We're just going to kind of think it through. If we start with a simple curve, like this, I know that this curve, it has an x value. What I'm going to do is I'm going to move over to my next point, right here. But I'm not going to call it x1 or x2. What I'm going to do is I'm going to call it plus delta x. In other words, I'm going to change my value by a certain amount. For example, if this was 3 and delta x was 2, this would be 3 plus 2, which would put me at 5. So my new point here becomes whatever my original x was plus this change in x. Now, these two x values have corresponding y values. There's f of x. There's f of x plus delta x. Right, like so. From here, I can solve for a tangent line. If I were to draw a line here, I can have a secant line, excuse me. This is a secant line, not a secant. That's like, oh, who lives in a pineapple under the sea? That's a secant. A secant line is any line that touches a graph in 2 points. What we're going to do is we're going to use what we know about the secant line to get the slope at exactly 1 point, or a tangent line. So let's start with the most basic. To get the slope of a secant line, it's our change in y over our change in x. Delta y over delta x. Let me use that for our new points over here. Hello. That got bold. Let me see here. There we go. Let's see if this works now. To get our slope of our secant line, I'm going to use these points. To get my change in y, it's my top y value minus my bottom y value. F of x plus delta x minus my original function, f of x, not delta, f of x. Divide that by the change in your x values. Well, my x2 is here. This is going to be x plus delta x minus x. And what happens is those x values cancel, and we're left with the following. F of x plus delta x minus f of x over delta x. Now remember, delta x is nothing more than my change in my x values. And what we have here now, on top, we still have our change in y, and the bottom, we still have our change in x. But there is a problem. Now this is my slope formula. Change in y, my change in my y values, y2 minus y1, over my change in my x values, x2 minus x1. It's just, we just have a delta x on bottom. Now the problem here is this still needs 2 points. So the question is, well, how do I get this down to 1 point? And that's where the brilliance of Leibniz and Newton come in. Newton and Leibniz. If we let delta x go to 0, if we let delta x go to 0, we get 1 point. Now, we can't let delta x go to 0 because we can't divide by 0. However, there is something that allows us to let delta x go to 0 without us actually doing it, and that's a limit. And that's what they did. They just took the limit as delta x goes to 0, and then they get this f of x plus delta x minus f of x over delta x. And that is how we get the slope of a tangent line. And this equation right here is monumental in mathematics, in physics. This equation right here allows us to calculate instantaneous velocities. It allows Doppler radar to work, which is how I get speeding tickets all the time. We can use this to find the maximum or minimum values of parabolas. There's so many applications for the derivative. In fact, we spend the entire first semester just talking about all those applications for that derivative. So what's really neat about this one, where if I just leave it like this, I need 2 points. But by taking that limit, now we only need 1 point. And most of you guys have already guessed, this is a special formula we call the derivative. So let's talk about the derivative. Now we're going to make it a little bit easier for us to work with. For example, we're going to use h instead of delta x. So we're going to let h equal delta x. And that just makes it a little bit easier for us to work with on these. Also, where f of x is a function, over here you see this little apostrophe right there. We call that a prime. And that prime means we're talking about a derivative. We have other notations. Newton liked the f primes. He didn't really like that. He actually used a dot, but they get kind of complicated. We also have y prime. Leibniz came up with this one right here, dy dx. Now, a lot of people mistake the d there for derivative. That is not what the d really is. The d is for delta. This is really saying, this is equivalent to saying the change in y over the change in x, but with 1 point. Delta y, delta x is 2 points, dy dx is 1 point. And if you're in computer science, you have a notation like this. These all read the same way. The derivative of y with respect to x. The derivative of y with respect to x. The derivative of a function with respect to x. So let's take a look at this example here. We're given the function x squared minus 4x, and we want to find the derivative of the function, and then use that to find the slope at x equals 3. Super easy to do. So to get our derivative, here, hold on here. To get our derivative here, we're going to say f prime of x equals long fraction bar. Whoop, see, I messed up already. Get rid of that. You need to have the word limit, and we're going to say h goes to 0. Now notice I put f prime because we're talking about a derivative here. The rule says everywhere there's an x, I'm going to plug in an x plus h. So I'm going to write this in brackets here. This becomes x plus h squared minus 4 times x plus h. Minus the OG, the original function, f of x. I use brackets because it helps me with the arithmetic. And this becomes x squared minus 4x, all over h. Now it looks nasty, but this cleans up pretty nicely, we're going to find out. So we have to expand x plus h squared. Now if you forgot that, let's go and do that up here. X plus h squared is just x plus h times x plus h. And if we distribute, we get x squared plus 2xh plus h squared. So I can rewrite this, the limit as h goes to 0, don't forget your limits. This x plus h squared becomes x squared plus 2xh plus h squared minus 4x minus 4h minus x squared plus 4x all over h. The x squareds will cancel. And what you're going to find out is everything that does not have an h cancels. And when I rewrite this, h goes to 0, 2xh plus h squared minus 4h all over h. And as many probably are aware, I can factor out an h here. Let me make the h look a little bit better. I can now factor out an h. And we get the following. As h goes to 0, h 2x plus h minus 4 over h. And those h's cancel. And if you're really good at the algebra, and you are, if I let h go to 0, this becomes 0, and we're left with our derivative. What's left? F prime of x is 2x minus 4. And there's our derivative. Now, this derivative has a very special meaning. It finds slope. That's all it does. It just finds slope. Remember, we got the derivative from the slope formula. So we proved that this is actually slope for us. Now, the last part of the question says, find the slope at x equals 3. All right, so the last part says, find the slope at x equals 3. To do that, well, this finds my slope at any x value, so I'm just going to plug it in. And here's how watch it. Watch the notation. F prime of 3 is 2 times 3 minus 4, which is just 2. This is amazing. What this says is, this shape right here is a parabola. If I were to graph that parabola, if we were to graph this parabola here, let's go ahead and do that real quick. We get x squared minus 4x, so x squared, whoops, can't we type it in first? X squared minus 4x. If I were to graph that parabola, this is saying at x equals 3, the exact slope at that point is 2. We'll talk about how to use a calculator on these later on this year. So go into the next video. We're going to take a look at a bunch more examples. I'll see you then. Bye-bye.